Assalamu alaikum. Today we'll be learning about the remaining things, chapter number 4, which is combinational electronics, and focus of today's part is going to be arithmetics. Um, we'll see binary adders, full adders, ripple adders, unsigned binary subtractions, binary adder subtractors, overflow detections, and some different techniques of multiplication and design by contraction. Let's start. Iterative combinational circuit arithmetic functions operate on binary vectors, use the same subfunction in each bit position, and one can design a functional block for the sub function and repeat it to obtain functional blocks for overall function. You can say that the circuit of a adder requires the same blocks that repeat again and again. Let's say if we have a 32-bit adder, so it will use 32 uh, portions of 1-bit adder. And the inputs will be different definitely, and the outputs are going to be different, and but the main computational block is going to be the same. So iterative array takes advantage of the regularity to make design feasible, and we use the technique of divide and conquer by simplifying the design to the primitive component and then repeating that primitive component again and again, and interlinking them uh, with these intermediate results. So binary adders, binary addition used frequently, additional development, full adders are required to make a binary adder. And in this regard we have two types of adders. One is the ripple carry adder, an iterative array to perform the binary addition, and CLA, a hierarchical structure to improve the performance of the addition. So block diagram of one day iterative adder. So, so let's see what is addition. This is important thing. We have seen this plus symbol, and it is very easy. 1 plus 1 is equal to, let's say, this is not a OR gate, simple addition. 1 plus 1 equal to 2, 1 plus 1 equal to 1 0. So two inputs, 1 bit binary adder that perform the following computation, and let's say we have like x, y, and the result is sum, and if the sum is big, it cannot be in single bit, the carry will be generated. So 0 plus 0, sum 0, no problem. 0 plus 1, 1, sum 1, carry 0, no problem. 1 plus 0, sum 1, carry 0. But 1 plus 1 equal to 2. So there is going to be a 0 here and a carry here. So carry is 1. So a half adder adds 2 bit to produce a 2-bit sum. The sum is expressed as sum bit and carry is as C bit. The half array adder can be specified as a truth table given below. And the same thing, 0 0 carry 0, sum 0, 0 1, sum 1, 1 0, sum 1, but 1 plus 1, sum is 0 and carry is 1, which makes it 2. 2 is written as 1 0 in binary world. Most common adder, half adder, is implemented in this way. From this equation, if we can see this, the sum is following the pattern of an XOR gate and carry is basically following a simple AND gate. So we can just implement this thing by using a XOR gate and a AND gate and get a half adder circuit for basic addition if our inputs is 2 bit. But what if we have a third bit as well? So let's say In the simplest aspect, we have, let's say, A, B, and let's say sum and carry, but we may have a third carry from the previous. Let's say a block generated a sum and a carry. The carry must go to the next module. This was like the initial module, answer of 0 or sum of 0. This is sum of 1. So this carry must go, carry must be forwarded to the next computational block. New A1 and B1 are going to be here. So this carry is going to be compensated in the next computational block. So this is where C in comes in, and sum and carry. So a half adder can be used in a zeroth bit of an adder, but there must be a full adder, adder with 3 inputs, A, B, and a carry in input, to proceed for advanced addition. So this is the case logic optimizer. Full adder as compared to half adder has a third input Ci, which basically takes the carry input generated from the previous structure, from the previous bit, and then we can just simplify this with a truth table, and we can make the truth table according to this K-map, and then solve and simplify our circuit for the final equation. So A, B, C, 0, 0, 0, all are 0. If any bit is 1, sum is going to be 1. If 2 bits are going to be 1, the sum is going to be 1, 0. So you can see here 2 bits are 1, the sum is 1, 0. Here 2 bits are 1, the sum is 1, 0. Wherever the bit is only 1, the result is going to be 0, 1, because 0 plus 0 plus 1 is going to be 0, 1. And if 3 bits are going to be 1, then answer is going to be 1, 1. 1 plus 1 plus 1 equal to 3. 3 in return in binary is basically 1, 1. So this is a simple truth table that takes the all possible inputs and outputs, and then we can just use a K-map to find these equations of sum and carry. And full adder schematic for I bit. So in this scenario, we have represented the full adder by combining the equations for the sum and for the carry, and this intermediate carry is basically generated carry, and these are the propagated carries, and the equation for carry is basically this thing: Ci plus 1 is equal to Gi plus Pi into Ci. So G is basically propagated carry, generated carry, and P is propagated carry. This information is going to be used in another advanced adder, CLA, for simplification. So we'll discuss that thing later on as well. So binary adders: to add multiple operands, we bundle logical signal together into vector and useful functional blocks that operate on vectors. So let's say we have this thing 1 0 1 1, and the other addend is 0 0 1 1. 1 1 is going to be 2. In binary it's going to be 1 0. 0 is at sum and carry is here. So 3 1 will make it a 1 in the sum and 1 in a carry. So 1 0 0 0 is going to be 1, only sum 1, no carry. 1 0 1, sum is basically 1, no carry. So this is basically your answer. Sum, you can say the 1 2 1 2 4 8. 8 plus 2 10, 11 plus this is 3, it's going to be 14. So 1 2 4 8, 2 4 is 6, 6 plus 8 is 14. So you can verify your answer by converting it into equivalent binary to decimal number, just to verify. So this is a solved example for a 4-bit ripple adder. 4 ripple carry made from 4 1-bit full adders. So once we have made a 1-bit full adder with 2 inputs AI and PI and a carry taking input CI, the output is basically sum of I, and the carry generated or carry is basically CI plus 1. This CI plus 1 is going to be fed to the Cin of the next module, and so on. So this is an iterative array, and similar block is used again and again, no matter how big the adder may be. Maybe the adder is 64-bit, and maybe in some application the adder is 1024-bit. It is possible, yes. In the world of logic design architecture, you can design anything that your system requires. So, but these adders are slow, mainly delay from input to output. So this delay from input to output it will increase as the number of parts number of array is going to increase. This carry chain is going to increase, and hence slow the final answer. So ripple carry adder, you can see if each individual block is taking 8 nanosecond to compute the answer, because again there are propagational delays inside the IC. If there is an AND gate, it will take a finite amount of time for this result to be translated at the output. For the sake of argument, this technology takes 8 nanosecond for a single full adder to complete its result at the sums and at the carry outs. There can be 4 cases, and which are discussed here, but the final output will take at least 32 nanosecond. This final carry out may take 32 nanosecond for this particular case, and if it's increased, this number is going to be multiplied by this particular factor. So some basic calculation: assume that AND and OR gates have 1 gate delay, and XOR has 2 gate delays, because XOR, we know that the XOR is comprised of 2 block A bar B plus AB bar. So XOR takes 2 gate delays and OR gates take 1 gate delay. So this is the equation for sums. Takes 2 delays, and 2 plus 2 4 delays, and carry will take 2 plus 3 delays and 4 delays. So delay of carry is going to be, let's say, computed by this in 8 10 delays. So the general equation that we can find out by this method, that carry is taking 4 delays and this is taking 2 delay, and then forwarding it, the general equation is 2n plus 2 delays for carry, and sum is 2n plus 4. So if you have 32 bit array, you can plug in the value of n equal to 32 in these two equations and get the approximate delay according to the IC technology that you are using. So example of 4-bit adder, n equal to 4, particularly 4 delays, 6 delays, 6, 8, 10. So we have we can use the previous formula and find these delays. Delays usually occur because of long chains of carry input and carry output. And one problem with the addition of binary number is the length of the time to propagate the ripple carry from the least significant bit to the most significant bit. This is the longest chain that will require that time. So a ripple carry has a unit gate array of 1 nanosecond. What is the total delay of the adder, and what is the max frequency at which it can be clocked? So these are two relevant questions that you need to answer. Answer is given in the slide set, but compute them by yourself and see. So it's going to be easy. What is the total delay of the adder? You can use those equations that we have seen previously. And what is the conclusion of this number that comes after this thing? The technology is 1 nanosecond, means for the sake of argument that our circuit will take 1 nanosecond for the input to output time. So this is the technology bottleneck. So whatever number comes out, you cannot go faster than that number. Let's say for the sake of argument this number comes out to be 50 nanoseconds, or let's say it comes out to be 100 nanoseconds. You can convert this number into 1 is equal to f 1 by t. You can get a frequency f. That is the frequency with which your computation is done. So if that computation frequency goes beyond a certain number, you cannot go faster than that frequency. Okay. So if it's let's say 1 divided by 100 nanosecond, we can compute it. So this is going to be 10 megahertz. So your design cannot be faster than 10 megahertz, and this is the maximum frequency that you can achieve. So use a different circuit to calculate the carry out, calculates it ahead to speed up the overall addition. This requires more complex circuits, and trade-off is that you will require speed versus area to have this fastness in your design. So a carry lookup adder basically computes the carry by using some common facts from the basic ripple carry adder, and it uses additional combinational logic, extensive circuits to make the carry chain faster. So more ICs for high speed. So some parts are the same. Let's say the half adder parts are the same as in previous A0, B0, and two types of sum are generated: a propagated and a generated carry, and a propagated carry. The yellow part is basic, where we design the combinational logic in the system, and there are some equations that we'll see. So CLA cases, there are 4 cases. So propagated carry means that the carry was generated from propagation of a carry from on the C in pin. So one was generated at the output here, and this carry, one of the reason is this pin, and carry generated 111. This carry is generated for both cases due to the propagation from a previous bit on the scene, and also by these two ones that generated the carry. So this case comes in both sections, and this is purely the case of a generated carry. Here is no propagated carry. So these are 4 cases, but we comprehend them in general. 2 carry. There are 2 types of carries: a generated carry and a propagated carry. So based on the analysis, we can now develop an expression for the output carry, C out, each full adder stage in 4-bit example. So carry out is composed of two things: carry generated, this thing, carry generated CG, and then or C in into CP, C in 1 into CP. So this is a general equation for the carry. These are the two possibilities for the carry. Carry in and carry propagated will be according to previous carry, and then carry will be propagated. So C in 2 is equal to C out 1. We know that C in 2 is going to be C out 1. Let's say you can say this is C in 2, C in 2, and this is C out 1. So both are the same thing. In the same way, C in 3 is basically C out 2. So this is the equation that we are going to use, that C in 3 is equal to C out 2, C in 4 is equal to C out 3. Okay, so C out is equal to CG2 plus CP2 into C in 2. In the same way that C out 3 is equal to CG3 plus CP3 into C in 3. So this is a general equation. So CG2 plus CP2 is equal to, because C in 2 is equal to C out 1, and we can plug in the value of C out 1 here. This is the same value to plug it here, and then we can open these values by normal multiplication. CP2 into CG1, CP2 into CP1 into C in 1. So we get the this is basically equation, but it is also a combinational circuit based on and OR gates. Same is the case with C in 3 is equal to C out 2, and C out 3 is going to be CG3 plus CP3 into C in 3. C in 3 is equal to C out 2, and we can plug the value from the previous C out 2 here, and then solve to multiply, and then we can take a C out 4 is equal to C in 3, C in 4 is equal to C out 3, and then open this equation. So usually we don't go beyond 4-bit because this equation gets more complicated, and rather than having advantage, we can get a disadvantage. So we basically make 4-bit CLA adders and use them and cascade them like the previous triple carry adders. So notice that each of these expressions, that output carry for the each full bit array state dependent on initial input, C in, the CG and CP function of the stages, and CG and CP function proceed the stages. So this was our 4-bit implementation, and as told earlier, that partial full adders were used, and then this combinational logic of carry generation and carry propagation was used, and this is again a more detailed diagram that makes those equations that we derive, makes a circuit out of those equations. So this is the yellow area that we saw in earlier block diagram, and these partial full adders were basically you can say they were like 1-bit adders that we saw there, half adders that we saw in the diagram. So this is the overall implementation of the carry loci adder, 4-bit carry loci adder. So this requires some time to understand, and because of this additional combinational logic, we get the result much faster than the results of a ripple carry adder. So other than this, we have unsigned subtraction, because it is very important we understand how addition and subtraction take place inside a computer, because now we are interested how this plus sign is basically implemented into a digital circuit. So we are making this plus sign operator, we are executing this plus sign to make the addition possible. So 4-bit numbers, unsigned subtraction, and this number is, let's say, 9, this number is 7, and simply you can just have this thing. 1 minus 1 is 0, and 0, we need to take a carry from the next bit. It's also 0, we need to get a carry from the next bit, so this will give a carry to it. So 2, this will be 2, and this will take carry from this will be 1. This is going to be 2. 2 minus 1 is going to be 1, and then 1 was here remaining, so 1 minus 1 is going to be 0. This was already 0 because the borrow was taken from it. So 9 minus 7 equal to 2, 4-bit number. So 4 minus 7 is going to be this number, which is wrong, because this is not the right way to do it. This is the wrong answer. If our m is bigger and n is smaller, the answer is okay. But if our number m is smaller and n is bigger, a borrow is generated. So if a borrow is generated, we need to have a compensation. So what is the compensation? So what happened with the previous example, we had to borrow 1, which corresponds to 2 to the power 4. Thus we actually added 2, 4 or 2n. To get the answer, we need to subtract the previous answer from 2n. So if this happens, we are doing the simple unsigned subtraction. We need to basically subtract our answer from this number. So this will give us the right result. This is going to be 2, 2, 2, 2, 2, 2 minus 1 is going to be 1, and because we have taken the borrow, this is 1, 1, 1, 1, minus 0 is going to be 1, 1 minus 1, 0, 1 minus 1, 0, and this was already 0 since we take borrow carry from here. So the answer is going to be 3, and we will have to add a minus sign to it. So algorithm, subtract the subtrahend n from the minus m minus n. If no n borrow occurs, then m is greater than n and the result is non-negative and number is correct. If n borrow occurs and m is less than n, and the difference m minus n plus 2 to the power n is subtracted from the 2n, a minus sign is appended to the result. So if a borrow occurs, you need to perform a additional step to get the answer, and then add a minus sign to it. So examples were basically covered. 8 minus 5 is going to be good, but 5 minus 8 is going to result in something like this number. So we need to subtract it from, let's say, a bigger number, 1 0 0 0 0, and then we can have the final answer, and we'll add a minus sign to it. So unsigned subtraction algorithm. So you can practice these things, because these are the way that the result is shown in these numbers, and we need to understand these numbers. So unsigned adder and subtractor. If you want to make an unsigned adder and subtractor, to do both unsigned addition and unsigned subtraction, complex circuit introduce, complement as an approach to simplify the next circuit. So this is how we do addition and subtraction. In general, the subtraction is not done in the way we perceive. Let's say we don't do the subtraction like 1 1 1 0, so 1 minus 0 is 1 and 1 minus 1 is 0. This is not the way we do the subtraction in the computer world. So we use the 2's complement method that we are going to select, and overall block diagram of these things are shown here. So two types of complements, diminished radius complements, defined as Rn minus 1 bracket close minus n with a number of digits, and these we'll shortly see these things how this work with an example. So this is our number, and the number is particularly this thing, and this is basically 1's complement. 1's complement is a similar number that if there is a number 1 0 1, its complement is going to be 0 1 0. This is the mathematics, this is the general way of solving this, but this is the whole mathematics, that if you want to take the 1's complement with the proper formula, you can apply this formula and get the complemented answer. So Rn minus 1, where this number is going to be represented by the maximum power possible, and then you subtract this number from that thing and you get a complemented number. So 2's complement is like the same process. You get the 2's complement with the formula that we discussed earlier, and then add a 1 to it. So if we have like a number like 1 0 1, we want to take its complement as 0 1 0. This is the 1's complement, which all bits are inverted or subtracted from the maximum power, and then we add a plus 1 to it, so 0 1 1 1 0. This is the 2's complement of this number. This is the 1's complement of this number. So given n bit binary numbers beginning at least significant bit and proceeding upward, copy all the least significant bit, copy the first, complement all the later part. So 2's complement example. So let's say we have any number 1 0 0 1 0 1 0 0. There are two methods for it. If you want to do a complete let's say 1 0 0 1 0 1 0. So one way is that 1 0 0 1 0 1 0 0. We take the 1 complement of it. 1 complement is going to be 1 1 0 1 0 1 1 0. This is 1's complement, and then we take a plus 1 add to it. 1 1 is going to be 0, 1 added, 1 1 is going to be 0, 1 here, 1 here. The remaining is going to be the same. So 0 1 1 0 1 1 0. This is the direct method, but if you want to apply, this is the method which we compute, not the direct method, and this is a shortcut method. So copy all the least significant zeros. We follow until there is a zeros. We copy the same thing until the first one comes, and then we basically complement the other bits. So we copy portion till here, and then we'll complement these things to 1 0 1 1 0. This is the direct method of taking a 2's complement. So binary complement, you can take the binary complement as discussed previously by inversing the bits and adding 1 to it, and this requires again practice. You should practice, and this is very easy, basic techniques, and these are. So if you want to subtract the number with 2's complement, it is like the process of addition. Rather than doing the a minus b, we if you want to do a minus b in computer, we'll do, let's say, a plus of 2's complement of b. These two procedures are basically equivalent. Okay. So if m is greater than n, the sum produces an n carry which is discarded from the above m minus n, and remain which is correct basically result. So if m minus n plus 2n, we write this thing as this thing, 2n minus n minus m, and we obtain the result. So let's see a example through which we can understand it better. So these are two numbers that we need to subtract, and the equivalent numbers are 84 and 67. So the number is basically 0 1 0 1 0 1 0 0, and the next number is this number. We take the 2's complement of this number, the second number. This is the 2's complement of this number. We add and the end carry is generated. So 0 1 1 0 0 0 1 1 0 1 1 1 0 1 triple 1 1 carry 1 1 1 0 1 1 1 0 1 1 1 0 1. So a carry is generated. That's a good sign. And we'll discard the carry, and the correct of result is the result is fine. You can see the result is 17. 1 2 4 8 16. 16 plus 1 is going to be 17. So this technique basically is very useful for directly computing the binary results. We know that 1 2 4 8 16 32, the power goes like this thing. So if a number is like 1 0 0 0 1, so if I have a number, I can just put these weights, very easy to compute, and then add the ones. 1 ones are 1 and 16 ones are 16. So this is equal to 17. This is direct way of seeing the binary variables in your answers. Very easy to compute. Let's say 67 minus 84. Now 67 is a smaller number, 8 minus 84 is a bigger number, so the answer is going to be different, and no end carry is going to be generated. So 1 0 1 1 0 1 0 1 1 0 1 1 0 0 0 0 1 1 1 0 1 0 1 1, no end carry is generated. So there is a problem. We need to correct this result by taking the complements, 1's complement, and then adding 1 to it and 2's complement. The final answer will have a negative sign associated with it. So this is our final answer, minus 17. So this is very important that you understand unsigned 2's complement subtraction, and then exercise this thing. There is no shortcut to exercise. So using 2's complement, the subtraction becomes an addition. This leads to much simpler circuit that we have seen previously, and addition is more doable. So this is how it's done, addition and subtraction. So let's say you connect these circuits in this form, and this arrangement is basically complement adder subtractor, and a plus b and a minus b both can be done. If sum is equal to 1, the answer is going to be subtracted at the output. If it's 0, it's going to be addition. So how this addition and subtraction is going to take place? Let's say we say that a is 0 0 1 1, a is 0 0 1 1, and b is 0 1 0 1. Okay, so we place the a's. A is, let's say I change the color for understanding. A is this 0 0 1 1, and b is in the you can say b is the red one. So this is basically 3, and this is 5. 3 and 5. So if we do, let's say, we place a 0 here, putting a 0 here will make it in addition mode. 3 plus 5 is going to be 8. 1 1 0, 1 carry 1, so 1 1 0 carry 1, 1 1 0 carry 1, so here 1. So we have the answer is 8, which is right, and 8. 3 plus 5 is 8. So how this done? This, we place a 0 at the mode control. Consider it like a 0. If it's a 0, it will do the addition. If it's a 1 here, it will do the subtraction. So 0, it's going to do the addition. So by placing the 0 here, how it's going to be done? This 1 is going to come here, this 1 is going to come here, this 0 is going to come here, this 0 is going to come here. So these are like programmable inverters or buffers. The reason for this XOR gate is to have the programmable buffers and inverters here. So since we remember that this basically, if we make this XOR gate truth table here, you can see 0 0 0 1 1 0 1 1, and the result of a XOR gate was something like this. So you can see if you take one bit as C and one bit as I, and when the C bit is 0, let's say, so whatever is at the I is at the output. I is following the B, and if this C is 1, whatever is at the input, the complement is at the output. So this complement is basically 1's complement. So if your XOR gate is in this mode, it will give you a 1 complement answer. So what I mean to say, let's solve this thing by 0 examples. If 0 is here, this 0 will make sure whatever is at the B0 comes as it is at this input of the full adder. So if it's a 1 here, the 1 will be here. If it's a 0 here, 0 will be here. If it's a 1, 1 will be here. If it's 0, 0 will be here. So 0 1 1 0 carry 1, 1 1 1 1 0 carry 1, 1 0 1 1 0 1, sum is 0, carries 1, 1 0 0, sum is 1, carry 0. So no add and carry generated, your result is good to go. This is an 8. So you need to understand this technique to understand how a full adder subtractor works by using a XOR gate as a programmable buffer. So if it was a 1 here, for the sake of argument, if it was a 1 here, this 1 would have changed to 0, this 0 would have changed to 1, this 1 would have changed to 0, this 0 would have changed to 1, because 1 was here. So whatever was at the input, the complement would have been at the output, and the result is basically 1's complement result is received at the input of the full adder. And then because when we do the subtraction, we put a 1 here instead of a 0, so this 1 will provide the same procedure as adding a 1 to the 1 complement answer. Hence your one operand is going to be the same, and second operand is going to be the 2's complement of the number. So if we put a 1 here, let's say one number is 5 and one number is 3, so the direct answer should be this thing. And let's say we apply both things here, and 0 0 1 1. So 0 0 here. Let me see what is available here. So 1 is 0 1 0 1, and the other is 0 0 1 1. So apply it here and you will get the result as the complement. If it's a 1 here, you're going to get a 0 here. If it's a 1 here, you'll get a 0 here. So 0 here, you get a 1 here. So 0, you get a 1 here. This 1 will lead to this one. The result is, this result is 1's complement, and adding this plus 1 at the C in will make it 2's complement. So 2's complement plus whatever was at the input 0 1 0 1, the result is going to be there, and carry is going to be generated, and once more we are going to take the 2's complement of the answer, and that answer is going to be the negative answer. So far we have focused on the addition and subtraction of unsigned numbers. For signed numbers, how to represent sign. One need one more bit for information for the sign. So sign plus magnitude and sign complements. Thus positive numbers are unchanged, negative number use one of the above methods. So if you have signed number, the previously we were talking about unsigned numbers and unsigned subtraction, but in signed numbers we have a range both in negative side and in positive side, and one bit is dedicated to the positioning of side. For positive number, this bit remains 0. For negative number, this bit remains 1. So in positive it's the same thing, but in negative the number is basically taken as 2's complement of the positive number. So you can say that in signed world, minus 8 is represented in this way, minus 7 is represented in this way. So we know that if we have a 4-bit word in signed world with the sign, so our range is basically minus 8 to plus 7. But if it was an unsigned world, range was from 0 to 15. Range remains the same, however the domains change. Here negative world is also available in your computation, but range is halved to plus 7. But in unsigned, you are having the range from 0 to 15. So represent negative numbers by its 2's complement, then add the number including the sign bit, discard the carry out of the sign bit. So if m is greater than n, m minus n plus 2n, ignore the carry out. Answer is in 2's complement. If m is less than equal to n, it is 2's complement of the negative number, take it. So from the complement of the numbers, you are subtracting and following the rules of the addition. So complement examples are what we discussed earlier as well. So what if we want to discuss the overflow occurs, there must be a circuit that defends how the overflow is going to be catered in the real circuit. Overflow can occur if two operands with same sign, so plus, both numbers are in plus and their answer is greater than the allowed width, then overflow will occur. Subtraction of the operand with different sign. So for n bit sign number, then max numbers are min, max, positive, 2n n minus 1 minus 1, and most negative number is minus 2n minus 1 to minus 1. So example, 6-bit digit bit sign number, max position 2 5 minus 1 is 31. Most negative numbers is basically minus 32. So these are the ranges for the R numbers. If the result of the addition or subtraction is outside this range, overflow will occur. Example of 6-bit numbers: 18 plus 15 is 33. So this cannot be compensated, so overflow will occur. So no overflow will occur if the number is within the range of the number. Overflow in the other courses like microcontrollers, there we have a special flag. If overflow is detected, a special flag is raised to determine that condition has detected, and you need to do something about this thing. So 18 plus 15, this is like 33. 0 1 1 1 1 0 1 1 1 0 1 1 1 0 1 1 1 0 1 1 1 sorry, this one is directly here. No end carry is generated, so your answer is okay. So wrong answer due to overflow. So because 18 plus 15 is going to be 33, and this cannot be compensated in this format. Sorry, this answer is not right, because these numbers cannot be compensated in this number of bits in signed aspect. So 18 minus 15 is the answer is correct, and no overflow is detected. 0 1 1 1 0 1 0 0 0 0 0 0 1 1 0 1 1 1 0 1. So a overflow is detected in this case. Correct answer, no overflow. So overflow detection requires this example is basically shown that the role of carry bits in overflow detection. The role of carry bits in overflow detection. So if if there is no overflow, same bits are basically 1. If overflow is detecting, there is a change in the carry bits of the last bit and n minus 1 bit. So overflow occurs when the carry into the signed bit is different from carry out of the signed bit. Carry into the signed bit is different from the carry out of the signed bit. Here carry in to the signed bit and carry out of the signed bit both are the same, so no overflow is detected. We need to somehow detect this change. If these values are different, we can detect that overflow has occurred. So we can use an OR gate, because the OR gate detects if there is a change between the carry in Cn minus 1 and carry out Cn. So if there is that thing, we can raise the overflow flag to 1, and carry will be generated as it was. So a carry generation, carry overflow detection can be catered by adding this circuit of overflow into the previous circuit that we have seen here. So we can add the carry overflow here, and let's say so we can do this thing. So this was basically overflow detection. So binary multiplication is an important thing as well, in which we multiply the terms a0 a1 to b0 b1. These are 2 bits. Let's say 1, this can be 1 0 1 1. So we can multiply these a0 b0 a0 b1, and then a1 b0 a1 b1, and then add them. So this requires AND gates and adders, and we can make a basically multiplier, which is a very important aspect for the computation in digital logic. So this is simple multiplier that you can generate or more complex multipliers can also be made, but the foundations of the multipliers are very simple. So you can use 4-bit adders to do the addition fastly, and hence have large multipliers. So test these exercises out. Other arithmetic functions convenient to design functional blocks by contraction, removal of redundancy from circuit to which input fixing has been applied. So incrementing or decrementing, multiplying by constant, division by constant, zero fills and extension, multiplication. So contraction is a technique for simplifying the logic in the functional block to implement a different function. The new function must be realizable from the original function by applying rudimentary function to its input. Contraction is treated here only for application of zeros and ones and not for x and x bars. After application of zeros and one, equation for the logic diagrams are simplified. So let's say we want to do incrementing, adding a fixed value to an arithmetic variable. Fixed value is often 1, which is increments counting up, and these are called increments. Or we can have a fixed value decrement as opposed to a increment, or we can have a multiplication or division by let's say a fixed number, shift left by 2. So we can use this rudimentary logic, and this basically is very easy to understand if we know the binary numbers. So if we shift the number 1 bit left and add a 0, this number is going to be multiplied by 2. So if it's for the 17, it is going to be 34. Okay, so we have a division in the same form. If it's a 4, if you shift by right, it is going to be a 2, and if you shift it left, it's going to be a 8. So this is a very simple technique that we can understand by understanding the binary numbers and their moments, and we can work around these things. This was it from chapter number 4, where we learn about addition, signed and unsigned numbers, their rules, simple to understand, overflow detections, and these were an addition adder, CLA, carry look adder, how these works, adder subtractors, and they are the basic foundational elements of computers. Addition and subtraction and multiplication, and all the theory related to these things are discussed in chapter number 4. Thank you very much. Allah Hafiz.